We feel it every single moment of our conscious lives. It determines how we move, how the planets revolve around the sun, and even how fast the hands of our clocks tick. From the simplest everyday experiences to colossal cosmic phenomena, gravity permeates everything. In a very real sense, the history of gravity is the history of physics itself. Yet, even after more than 400 years of intensive scientific research, we still do not have a clear, ultimate answer to what it actually is. In this script, we will explore how humanity journeyed toward our modern understanding of this invisible bond, and why a phenomenon we can measure with such breathtaking precision still hides its deepest secrets. This story does not begin with an apple falling on someone's head. Long before the scientific revolution, ancient Greek and Indian philosophers observed that raindrops and heavy objects naturally fall toward the earth. However, classical thinkers like Aristotle did not believe this pull extended to celestial bodies. To them, the heavens were a realm of perfection, completely separate from earthly laws. Aristotle argued that celestial objects possessed an inherent, natural motion that kept them moving along eternal, circular paths without the need for any external forces. On Earth, however, objects sought their natural place, which was the center of our planet, believed at the time to be the absolute center of the entire universe. For centuries, the dominant scientific dogma claimed that for any object to maintain a constant speed, a continuous force had to be applied through direct, physical contact. The concept of an invisible, non-contact interaction acting across vast distances was entirely outside their philosophical framework, stalling physical science for nearly 2 millennia. The Great Awakening came in the 16th and early 17th centuries. Armed with the heliocentric ideas of Nicolaus Copernicus, the German astronomer Johannes Kepler set out to map the heavens by meticulously analyzing planetary data. Kepler described the orbits of planets using elegant geometric and mathematical laws. He discovered that planets do not move in perfect circles, but rather along elliptical paths, and that their orbital speeds depend directly on their distance from the Sun. Kepler's work was a monument of early science, proving that the solar system operated on predictable mathematical rules. Yet, Kepler could not explain why the planets moved this way. To solve that mystery, the world needed the genius of Isaac Newton. Whether an apple truly triggered Newton's realization remains a subject of debate. History is full of legends, where monumental theories appear in a flash of sudden inspiration, while the story of an apple hitting his head is almost certainly a myth. We do have the reliable account of John Conduit, Newton's assistant. He described how in the autumn of 1666, a 23-year-old Newton sat reflecting in his mother's garden at Woolsthorpe Manor. If you are enjoying this deep dive into the forces that shape our cosmos, please take a moment to like the video, comment on the video, and tell us where you are watching from today. We love seeing how far our community reaches across the globe, and your support helps us bring more of these incredible scientific journeys to life. Now, let us return to the garden at Woolsthorpe as Newton watched an apple fall. His mind leapt far beyond the orchard. He realized that before falling, the apple's velocity was 0, but as it dropped, it accelerated. Therefore, an invisible force must be acting on it to cause that acceleration. He named this force gravity. But then came his truly revolutionary thought. Did this force have a limit? Did it stop at the top of the apple tree? Or perhaps at the peak of the highest mountain? Could this same force reach all the way to the moon? If gravity extended into the heavens, there had to be a mathematical connection between the way objects fall on Earth and the way the moon orbits our planet. This was a mind-bending leap for the 17th century. Newton connected earthly falling with celestial orbiting, realizing they were caused by the exact same mechanism. But why doesn't the moon crash into the Earth like the apple? To explain this, Newton envisioned a giant cannon on top of an incredibly tall mountain, firing a cannonball parallel to the ground. Without gravity, the cannonball would fly off into space in a straight line. With gravity, the ball curves down and hits the ground. If you fire the cannonball with greater speed, It travels much farther before landing. Finally, if you fire it with just the right velocity, the curve of the cannonball's fall will match the curvature of the Earth. The cannonball will fall perpetually around the globe, never touching the surface. The Moon, Newton realized, is simply that cannonball, falling forever around the Earth, but moving too fast horizontally to ever land. To turn this brilliant concept into a rigorous physical law, Newton needed a mathematical proof showing how gravity changes with distance. Using the known distance to the Moon and its orbital period, Newton calculated the Moon's acceleration. He found that the Moon experiences a tiny gravitational acceleration of only 0.00 to 7 meters per second squared, which is 3,600 times weaker than the gravity we feel on Earth. Since the Moon is 60 times farther from the center of the Earth than we are, and 3,600 is 60 squared, Newton discovered the famous inverse square law. The force of gravity decreases with the square of the distance. With his inverse square law established, Isaac Newton transformed the study of physics, but his equations were still missing a crucial piece. To calculate the absolute force between any two objects, scientists needed a constant multiplier representing the fundamental strength of gravity. It was only in 1798, more than 70 years after Newton's death, that Henry Cavendish measured this tiny number using a highly sensitive torsion balance. The gravitational constant, big G, turned out to be incredibly small, 6.674 times 10 to the minus 11th power. This tells us that gravity is actually the weakest of the fundamental forces. We only perceive it as strong because we live on a planet of colossal mass. Despite the success of Newton's law of universal gravitation, it possessed a major philosophical flaw. His theory required gravity to act instantaneously across empty space. How could the Sun exert a pull on the Earth millions of miles away without any physical medium between them? Critics accused him of introducing occult, magical forces. Newton agreed with their concerns, writing that gravity passing through a vacuum without a mediator was an absolute absurdity. Yet, because his mathematical formulas worked perfectly to predict the tides, the comet of Edmund Halley, and planetary orbits, science accepted his model. For nearly 2 centuries, the path to resolving this mystery began with a completely different force. In the 19th century, James Clerk Maxwell formulated his groundbreaking theory of electromagnetism. Instead of objects pulling each other through empty space, Maxwell explained that electric charges and magnets create fields that fill the surrounding space. Crucially, disturbances in an electromagnetic field do not travel instantly. They propagate as waves at the speed of light. This inspired physicists to wonder, could mass create a similar gravitational field that fills the universe, carrying gravitational influence at the speed of light? At the same time, scientists began to look closer at a unique property of gravity first noted by Galileo Galilei: the fact that all objects, regardless of mass or material, fall with the exact same acceleration when there is no air resistance. This was demonstrated on the airless Moon in 1971, when Apollo 15 astronaut David Scott dropped a hammer and a feather, watching them strike the ground at the exact same instant. In physics, this is known as the weak equivalence principle. It suggests that gravity is uniquely universal. It affects all matter and energy in the exact same way, implying that gravity might not be a traditional force at all. In 1905, a young patent clerk, Albert Einstein, shook the foundations of physics with his special theory of relativity, which unified space and time into a single four-dimensional fabric. 2 years later, in 1907, Einstein experienced what he called the happiest thought of his life. He realized that a person falling freely from the roof of a house would not feel their own weight. To explore this, Einstein imagined a person inside a closed elevator cabin. If the elevator is in deep space, far from any stars, the occupant floats in weightlessness. If the elevator is falling freely toward the Earth, the occupant also floats. No experiment performed inside that cabin can tell the occupant whether they are in empty space or falling in a gravitational field. Einstein concluded that gravity and acceleration are equivalent. meaning gravity must bend light. Since light travels straight, he realized that spacetime itself must be curved by mass. In 1915, his general theory of relativity replaced Newton's force with this geometry. As John Wheeler summarized, spacetime tells matter how to move, and matter tells spacetime how to curve. Thus, a falling apple simply navigates a straight path through a warped universe. Today, general relativity is proven by satellite time dilation and the 2015 discovery of gravitational waves. Yet, our understanding remains incomplete. Until we can reconcile Einstein's curved spacetime with subatomic quantum mechanics and the hypothetical graviton particle, gravity remains our deepest cosmic mystery.